Hi, welcome back to part 2, area between curves. So let's take a look at an example of one where we are between in terms of y. Now these are kind of hard to do, a little bit different. So we have a parabola, but this time it's a sideways parabola, and we have another line. So I want to graph this. So this one's a parabola in terms, it's not too bad to do. So when I graph this line, this parabola right here, its x-intercept is 5, it's negative y squared. So I know it's opening up to the left. This one's a little bit trickier to graph it. Now one, I could just solve for y, make it y equals x minus x plus 1. Or another way we can graph, and you probably haven't done this one, done this method in a while, is just using the intercepts. And that's what we go here at head view right now. So I'm going to let x be 0. If I let x be 0, y is 1. And if I let y be 0, x is negative 1. And I can graph it from here. So negative 1, 0, and 0, 1. So it looks kind of like this. Now if you notice my graph, I'm looking for the bounded area. I really don't have something bounded, but if I keep going, eventually those two are going to run into each other. And so this is our bounded region. Now keep in mind, we are in terms of y this time. So since we are in terms of y, our rule says we're going to use a, oh, hello, let me get my light back on here. There we go. Because we're in terms of y, our rule says to use a vertical, not a vertical, but a horizontal rectangle. So we're going to use a horizontal rectangle this time, and I'm going to draw that. So my rectangle, I draw it anywhere on the graph. It doesn't matter where you draw it. There's my rectangle. Right there. Now, in next step, I'm going to blow up the rectangle. There it is. There's my rectangle. I'm going to blow it up. Remember, it has a thickness this time because we're in terms of y. If you think about it across the y-axis, this right here is my change in y, dy. Oh, just like when we did differentials, there's my change in y. This will be my change in my x values. So the length is really just the change in your x values. And in this situation right here, all we're going to do there is just look at the right side minus the left side. Remember, always pick the bigger one minus the smaller one. So we're going to choose the right minus the left, like so. Well, the right side puts me on the parabola, which is this 5 minus y squared. Now notice I always put it in parentheses because I'm going to have to simplify. And the left is our line. See, here's our pick left hand, right hand. Right minus left. Literally, right hand minus left hand. Minus the line, which is this y minus 1 right there. Now I can simplify that. And if you do, you just get, what, 5 minus 1? Or 5 plus 1, I get 6 minus y squared minus y. So if I want to find the area of this one rectangle, it's going to be the length that we just found. 6 minus y squared minus y times the height of our rectangle, which is dy. So to get the exact area, remember, to get the exact area, we're going to integrate. Because remember, there's infinitely many rectangles. It's like basically this. Here's a rectangle down here, and we're going to take all these rectangles and we're going to add them all up. And remember, an integrand symbol really is an S, standing for sum. It's the sum of all of these rectangles that we made. So we get the 6 minus y squared minus y dy. Now notice I don't have the domain yet, so I do have to find out where they meet. But remember, we're in terms of y this time, so be very careful. So to do that, I'm going to take this 5 minus y squared equal to y minus 1. Find out where they meet. And that's putting the y squared over, plus y, minus 6 equals 0. Factor y plus 3, y minus 2, I get negative 3 and 2. So we're going to go from negative 3 to a positive 2. And that's where they meet at. And that's my domain. Remember, order is important. Smaller number on top, followed by the 2 up there. Okay? Next, I integrate. This becomes 6y minus y cubed over 3 minus y squared over 2 from negative 3 to 6. And if you apply the FTC, f of 6 minus f of negative 3, we can get our exact answer. You don't need to simplify. This will be fine. Just go 36 minus, whoops, this should be a 2. Definitely not a 6. Should be a 2. I don't know where we got the 6 from. There we go. Oh, wow, that makes it much nicer. So we get 12 minus 8/3. Again, minus 2. And plug in the negative 3. Negative 18. This becomes plus 9. And plug in the 3 over here. We get minus 9 over 2. You can leave your answer like this. I like that. Or if you want to simplify it, 125 over 6. And there we have it. Very easy to do. Remember, it's just finding the area of a rectangle. But here's how I'm going to point this out. Ready? You need to have your rectangle. You need to tell me where they meet. You need to have your integral. And, of course, your answer. Okay? I'm looking for that rectangle. All right. How can we use a calculator to solve these? Very nice. The inspires are very nice for these, okay? Anything that you can graph on. So we want to find the area bounded by the function x squared and x plus 1. So we are in terms of x. So I'm going to graph it. That's what I'm going to do. I'm just going to graph them. Go to graph. Graph my two functions. Up, doc, b. Clear out anything in there. Never trust anybody else's answers. Doc b, I'm going to graph it. I get x to the 6. X to the 6. Enter. Tab. And if I graph the other one, x plus 2. Enter. There we go. So I'm just going to sketch it. X to the 6 looks kind of like this. And x plus 2 like here. So where's our region bounded? Yeah, right in here. There's our bounded region. Calculus will make this a little bit nicer, but there's still some work you have to show. One, you have to show your rectangle. Now we are in terms of x. Remember what that means. We will have a vertical rectangle. Okay? We have a vertical rectangle. So I'm going to draw my rectangle. There it is. There's my vertical rectangle. Show it on here. Remember, I'm finding the area of this rectangle. I just blew it up. Okay? It has a width dx. Look at this. If you look at the rectangle, this is the change in x. But it's so small, we just call it dx. Remember, dx is very tiny. This is my change in my y values. Well, I can get my change in my y values because that's just going to be the top function minus the bottom value. Right? If I knew this was 5 and this was 3, the height would be 2. I would just subtract them. Same thing here. So my top is my line. I'm going to write that out. X plus 2 minus the bottom, which is x to the 6. Which is just x plus 2 minus x to the 6. So I'm looking for that. Next, I want to find out my area. My area of my one rectangle is going to be x plus 2 minus x to the 6 dx. And that's for one rectangle. Remember, to get them all, we are going to integrate this. Now again, you can get points for this, but there's still something I'm missing. I'm missing my domain. I'm missing where they meet. So to do that, I set them equal to each other. Like so. Now, unfortunately, I can't solve this by hand, but I have my calculator. I can use my calculator. Just go to Menu, Analyze Graph. I'm looking for where they intersect. For lower bound. I think if I just hit the middle here, I can scroll over. There's one of them. It looks to be at -1. And if I scroll over here, there's the other one. 1.215. And that's what I put in here. -1 to 1.215. And now I can calculate that area. And I'm going to do that in the home screen, homies. Math 4.2. And I just type it in exactly as it looks. -1 to 1.215. I just type in my equation. X plus 2 minus x to the 6 dx. I hit enter, and we get 3.96 7. And there's our area. Look how much work. Even if it's a calculated question, one, I'm still looking for that rectangle. I'm still looking for that equation, where they meet, our answer. That's what I'm looking for in these. Alright, so our last one, very simple, our last one is trying to find the integral of something like this. I call this the Sunglass Problem. Now if you notice right here, we have two functions, f of x and g of x, but they intersect each other, but they also, look what happens here, they switch to top and bottom. So because the top and bottom switch, we actually have to make two integrals. So for this one, we will need two integrals, and it's not hard to do. Okay? We are in terms of x, so we're talking about vertical rectangles. So if I draw my two rectangles, here's one rectangle. But notice, it stops at C. So it's like it starts at A, it goes to C, I'm talking x values here because we're in terms of x, and then it goes and ends at H. So what we're going to do is we're going to make one integral that goes from A to C, and then another integral that goes from C to H. So how do we do that? Very simple. Let's deal with our first rectangle. Our first rectangle, again, it has a width of dx. Its height, remember, top minus bottom. The top of this part right here is g of x minus the bottom, which is f of x. So this area of this region right here that we're looking at will have an area of g of x minus f of x, the values of g of x minus f of x. And it's going to go from starts at A, ends at C. So from A to C. Next, I have this region. Well, I draw another rectangle. Since I'm in terms of x, again, it'll be vertical. And I draw it again. I'm looking for those rectangles. It has a width, again, of dx. To get the height, this time, f is on top and g is on bottom. So we have f of x minus g of x. So to get this area, we're going to take f of x minus the g of x. Don't forget to multiply by the dx, the length times the width. That's literally what we're doing. Area of a rectangle, length times width. And this one starts at C and goes all the way to H. And what do you suppose we do with these two? Yeah, we just add them together. A little bit longer to do, but add them together. So there you have it, area between two curves. Hope you guys enjoyed the lesson as much as I enjoyed giving it. And I'll talk to you later. Bye-bye.